Hello friends, welcome back to my YouTube channel. So in last video we have solved a problem of non-sway frame by using the stiffness method. Today we'll see the one more problem of non-sway frame by using the stiffness method. So this is the given frame. So here, as usual, our first step is to find out the degree of kinematic. So now we'll see without wasting the time. So here our at fixed end dk0, at this point B our degree of dk is 1, and here at this support in support our dk value is 1, and call it as the coordinate number 1, and this is the coordinate number 2, and this is our first step. So step number 1, our dk is 2, so call it as the at point B theta b, and at point C it is theta c. And our second step, or step number 2, is the giving name to the coordinates. So I gave here coordinate number 1 and 2. And our third step is to find out the stiffness coefficient. So for that, when we apply the here, this is our coordinate number 1 and this is our coordinate number 2. So when we apply the unit rotation at coordinate number 1, what happens, we'll see. So when we apply the unit rotation at coordinate number 1, so our deflection curve will be like this, and here the force generated will be 4EI divided by L. Here also 4EI divided by L. It rotates clockwise, it also rotates clockwise, and the force generated at the coordinate number 2 due to this unit rotation at coordinate number 1 is half of this, carryover is half of this. So 4EI divided by L, so half of this is 2EI divided by L. So here K11 is nothing but force developed at coordinate number 1 due to the unit rotation applied at coordinate number 1. Here K21 is nothing but force developed at coordinate number 2 due to the unit rotation applied at coordinate number 1. So here K11 is nothing but summation of these two. So 4EI divided by length of the span AB and 4EI divided by length of the span BC. So substitute the all the values. So LAB length is 4 meter and BC length is 4 meter. So substitute that value, it will come out as 2EI. And similarly our K21 is equal to 2EI divided by length of this CB. So length of CB is 4. Substitute that value by simplifying, it will come out as 0.5 EI. So now we'll see. So when we apply the unit rotation at coordinate number 2, so what happens is the deflection curve will be like this, and the force generated at coordinate number 2 due to the unit rotation applied at coordinate number 2 will be 4EI divided by L, and the carryover force from here to here is half of this is nothing but 2EI divided by L. So K22 is nothing but 4EI divided by L. L is nothing but length of this span CB. So length of CB is 4 meter. So it will come out as EI. And similarly our K12 is nothing but force developed at coordinate number 1 due to the unit rotation applied at coordinate number 2. So it is 2EI divided by L. So L is nothing but our length of the span CB. It value also comes same as 21. K12 is equal to K21. So it will come out as 0.5 EI. This is how we need to find the coefficient of the stiffness matrix. So now our next step is to determine the stiffness matrix. So our dk value we got was 2. For that we have the matrix 2 into 2 matrix. We need to use this matrix. So step number 4 is find out the K matrix. So this is our formula. So substitute all the value. K11 we got was 2EI, and K12 we got was 0.5 EI, and K21 we got was 0.5 EI, and K22 we got was EI. And this is our K matrix. This is how we need to find out. And our next step is to, step number 5 is to find out the fixed end moment. So we have already solved how to find the fixed end moment while solving the problem by using the slope deflection method as well as moment distribution. So now one more time I will explain how to find the fixed end moment for each span. Here our span AB is carrying the point load of 20 kN. for the span which is carrying the point load. To find out the fixed moment of that, we have the formula. We have the formula for point load which is carrying the point load at center, which is acting at the center. For that, we have the formula MFAB is equal to minus WL divided by 8 and MFBA is equal to WL divided by 8. By using these two formula, we will calculate the fixed moment for AB as well as BA. So, MFAB is equal to minus WL divided by 8 here. Minus load is 20. Load is 20 and length is 4. 2 plus 2 is 4. Load is 20 and length is 4 divided by 8. Simplify it, it will come out as minus 10 kilonewton per meter. Similarly, for MFBA, we have the formula, same formula, only sign will change. So, it will come out as 10 kilonewton into meter. And now for MF span BC. So, span BC is carrying the UDL. So, for the UDL, we have the formula to find out the fixed end. We have this formula MFAB is equal to minus WL square divided by 12 and MFBA is equal to WL square divided by 12. By using these two formula, we will calculate the fixed end moment for span BC as well as CB. MFBC is equal to minus WL square divided by 12. So, minus here load is 20 and length is 4 meters. Substitute these values in that formula. Load is 20, length is 4 divided by 12. Simplified, it will come out as minus 26.66 kilonewton per meter. Similarly, for MFCB, the formula is same, only sign will change. WL square divided by 12, it will come out as 26.66 kilonewton per meter. So, this is how we need to find the fixed end moment for each span. We wish to find out the P matrix. So, we have the 2 into 2 matrix, TK number is 2. So, we need to use this matrix. P is equal to P1 plus P2. Now, we will see. P1 is nothing but total fixed end moment at first coordinate and P2 is nothing but total fixed end moment at second coordinate. So, now we will see. So, our first coordinate is at point B. So, here how many fixed ends are there at point B? MFBA plus MFBC. So, our P1 will be MFBA plus MFBC and our P2 is nothing but how many fixed end moments are there at coordinate number 2. So, here only one fixed end moment, that is MFCB. So, now we will see. So, our P1 is equal to MFBA plus MFBC. So, MFBA value we got was 10 and our MFBC value we got was minus 26.66. So, by simplifying, it will come out as minus 16.66. Similarly, our P2 is MFCB. We have this value. So, MFCB value we have is 26.66. So, now put here P is equal to P1 is minus 16.66 and P2 is 26.66. This is our P matrix. So, now our step number 6 is completed here. Step number 7 is to find out the theta coordinate. So, by using this equation, we'll find the theta coordinate. So, now we'll see. So, now substitute K matrix, the value we got when theta and P matrix, but K matrix value we got was, so we got K matrix is 2EI. So, I will write here. Substitute all the value we got was 2EI and 0.5 EI and 0.5 EI and EI. And theta value is nothing but short coordinates theta B and theta C. Theta is nothing but theta B and theta C is equal to minus P matrix is, so this one minus 16.66 and 26.66. So P is minus 16.66 and 26.66. So now we need to solve this 2EI into theta B. So now multiply 2 EI theta B plus 0.5 EI theta C, 0.5 EI theta C is equal to minus into minus plus 16.6 is call it as equation number 1. Similarly 0.5 EI theta B, 0.5 EI theta B plus EI theta C, EI theta C is equal to minus 26.66. Minus 26.66. So call it as equation number 2. So now we need to find the EI theta B as well as EI theta C. So by using these two equation we will find the EI theta B value as well as EI theta C. So by using calcium I will show you. Number 5 and 1. So now substitute 2 EI theta B, 2 is equal to 0.5 is equal to 16.66. 16.66 is equal to, and our equation 2 is 0.5 is equal to 1 is equal to minus 26.66. Minus 26.66. Now solve it. Our x value is nothing but EI theta B value. It came 17.137. So now write it here. EI theta B value is 17.137. Now solve it for the second time. Y value is nothing but EI theta C value. It came out as minus 35.22. Minus 35.22. So now this is our step number 7 is complete here. Our step number 8 is to find out the final moments by using the slope deflection equation. So by using these two formula we need to find the final moments. So our formula is MAB is equal to MFAB plus 2EI divided by L, 2 into theta A plus theta B minus 3 delta divided by L. So if they given in deflection value then only we need to use 3 dou divided by L, otherwise we need to neglect it. So our MBA is equal to fixed end moment of BA plus 2EI divided by L into 2 into our first point is B, so 2 into theta B plus our second point is A, so theta A minus 3 divided by L. So by using these two formula we need to solve the final moments. Now we will see. Step number 8 is to find out the final moment. So I have written the formula here. MAB is equal to MFAB. Fixed end moment of AB. Fixed end moment we got was minus 10. Put it here. Minus 10 plus 2 EI. Length of the AB. Length of AB is 4 meter. And here theta A is the fixed end. At fixed end slope becomes 0. Here point A is the fixed end, so at fixed end slope is 0, so that's why it becomes 0. And theta B value we got was 17.13. so now by simplifying our MAB value will come out as minus 1.43 kilonewton per meter. Similarly for MBA, so I have written formula, substitute all the here. MFBA value we got was 10 plus 2EI divided by length of BA we got was 4, and theta 2 into theta B is 17.13. Theta A is fixed and the value becomes 0. So now simplify it, it will come out as 27.13 kilonewton per meter. Similarly for BC, MFBC fixed moment of BC we got was minus 26.66 plus 2EI divided by length is 4 meter. 2 into theta B value is 17.13 plus theta C value is minus 35.22. So simplify it, our MBC value will come out as minus 27.14 kilonewton per meter. Similarly for MFCB value we got was 26.66 plus 2EI divided by length is 4 meter. 2 into theta C value we got was minus 35.22 plus theta B value is 17.13. So now simplify it, our MCB value will come out as 0.005. So it is nearly equal to 0. So this is how we need to find the final moments. So here our step number 8 completes. So next step is to drawing of the BMD. So now we'll see. So I have already drawn the pre-body diagram of this. Our span AB is carrying the point load. So for the point load we have the pre-body diagram like this triangle. So to find out this maximum we have the formula WL divided by 8. So WL divided by 4. WL divided by 4. So WL divided by 4, substitute all the value. The maximum height of this will come out as 20. For our similarly for BC is carrying the UDL. For UDL we have the pre-body diagram like this parabola. To find out this maximum we have the formula WL square divided by 8. So substitute all the value, it will come out as 40. Maximum height of this is 40. So this is our pre-body diagram of UDL. So now we'll see the net bending moment. So by using these final moments value, we'll draw the net bending moment. See here our AB, MAB. Here first point is A. So at point A, our value is minus 1.43. So at point A, one more thing, sign convention is this is A, this is B. Here minus plus minus. At point A, negative value comes above the neutral axis, means it comes here. It is minus 1.33, 1.4. Minus 1.4 means it comes nearly here. 1.43. And our MBA value we got was 27.13. So it is positive at point B. Here first point is B. No, at point B 27.13. So at point B positive value comes above the neutral axis, means it comes here 27.3. And similarly for MBC, first point is B, at point B value is minus 27.13. And for BC also, here minus, here plus, here plus, here minus. At point B negative value comes above the neutral axis. Our value is minus 27.1. Minus means it also comes here 27.14. It comes here. And last MCB, our value is nearly equal to 0. It comes here. So now join all these lines. So this is our bending moment diagram. So here remaining portion is positive, here also positive. So this is negative, this is negative. So this is how we need to draw the net bending moment diagram. So here our problem ends. So if you like the video, like it, share it and subscribe for the more videos. Thank you for watching.